Hi students! So we can't be together over Zoom today, so I've made a little homework video trying to answer your questions about polar area. If you have other questions or you have different questions after watching this, just feel free to send me an email or a message on Schoology, and I'll do my best to get back to you relatively quickly. So most of you had questions about this last problem, this last example, and specifically, like, why do we divide by the interval? Like 3 pi halves minus 0, why are we dividing by that? So that's where I'm going to spend my focus. So since there wasn't any questions about the setup, let's just go back. We'll jump into where Mr. Schulten said, okay, we have 1/2 0 to 3 pi halves square root squared d theta. And then he said we need to divide by 3 pi halves minus 0 because we're trying to find the average, right? Okay, so why divide? I'm going to take a step back. So when we're trying to find the average of, let's say, the numbers 2, 5, and 10, what we'll do is we'll say 2 plus 5 plus 10, and then we'll divide by the number of numbers we're adding. So that dividing by the number of numbers we're adding isn't really going to work for us in this case because we should be adding infinite numbers. So what I mean by adding infinite numbers is I mean this integral. So let's take it back to the limit definition of the integral. That looks like this. The limit as n is approaching infinity of the sum going from, let's say, k equals 0 to n of f of x sub k, so wherever we are at in that interval, times b minus a over n. And this was the width of each rectangle is going to be b minus a over n. Now, if we stop and take a pause, what does each part mean? The b minus a over n, that tells us, the width of each rectangle, because b and a are the sort of endpoints of the interval, and n is the number of rectangles we're using. And we can see that we're trying to get those number of rectangles go to infinity. Now, if we also take a step back and think back to last semester, we learned that the average value formula, so the average value of f, we can get that is the following. So the average value of f is equal to the integral from a to b of f of x divided by b minus a. So let's try to work backwards here. We talked about how when we want to find the average value of something, we're adding all the outputs. And then we need to divide by the number of things we've added. The number of things we're adding is really equal to the number of rectangles we break the area into. And going back to our limit definition, this is equal to n. So we should be dividing all of the numbers we're adding divided by n. But that's not what we did. We divided by the interval. So let's see why that makes sense. So if we take this average value formula, and instead of writing the integral, let's write the limit definition, we'll see something cool. The limit, Sorry if you hear that, that's Albus, he's a little pooped, too many walks today. And then I'm going to multiply by 1 over b minus a instead of dividing. Same thing. Okay, so let's take a look. All right. Well, b minus a, I can restructure this a little bit because the sum here the dependent variable, the thing that's changing, is actually k. So what can I pop out? We can actually pop this part out here. 1 over b minus a times the limit of b minus a divided by n times the sum going from k equals 0 to n of f of x of k. Okay, so let's take a pause and think, what is each piece telling us? This is saying we're adding up all the outputs of f of x from f of x sub 0 to f of x sub n. Remember, looking at all those different rectangles, this piece here is telling us the width. But again, let's stop and pause and think now. The limit statement, the variable that's changing is n. That's this part here and this part because of the n here. But it's not actually affecting b minus a. b minus a will be b minus a no matter what, so we can pop that part out as well. And I'm just going to do the limit of blah, 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 and we'll actually see, oh, hey, look, b minus a divided by b minus a, that's equal to 1. So what are we really left with? We're left with the limit, as n is approaching infinity, of the sum, going from k equals 0 to n of f of x sub k, divided by n. Don't forget this. And so let's take a minute and actually like regroup. What are we trying to do? We're trying to show how these pieces connect. So here, this is the number of things we're adding, or sorry, this is the things we're adding up. For example, like 2, 5, 10. And in our denominator, n is the number of numbers that we've added up. For example, 3. And so when we take this limit, we're actually getting an average. And it all comes back to, we needed to divide by our interval to sort of undo multiplying by an interval in the integral itself. So that's where that division part comes from. I'm going to pause for a second. Please, if you need to take a screenshot of this, take a picture, do it, because I'm about to erase it so that we can, or rather move it down and make it nice and small so that we can continue to solve the original integral in purple/green. Okay, making that very small and off to the side. Let's change all this to purple. Isn't this fun? Okay. All right, so let's evaluate this. There were a couple of questions about like, can you do this because I missed something somewhere and I'd like to check my work. All right, fair enough. So we have 1/2 times 1 over 3 pi halves. We're just moving this up. Times the integral from 0 to 3 pi halves. Square root squared is just theta, d theta. Equals, okay. Well, let's look here. 1/2 times 3 pi halves. 2 divided by 2, that's 1. So we have 1 over 3 pi. Going from 0 to 3 pi halves. Theta, d theta. And now let's evaluate that integral. The antiderivative of theta is theta squared. Don't forget. Reverse power rule, 1/2, going from 0 to 3 pi halves. And now it's just a matter of plugging in. We'll keep that 1 over 3 pi out. We have 1/2 times theta squared. Now, this is where you maybe have a mistake. Don't forget to square the whole quantity. Minus, well, when we plug in 0, that ain't gonna affect anything. 1/2 times 3 squared is 9, pi squared is pi squared, and don't forget to square your denominator as well, 4. And let's go and see what is going to divide to 1. Pi, and one of the pi's, we have pi times pi, so goodbye one of them. 3, and one of the 3's in here. And then that's still just 3 pi in our numerator. 1 3 left, 1 pi left. And the 2 and the 4 are still there as well. So 3 pi eighths. That was fun. I hope you enjoyed that. I am going to answer a couple more questions. They are the following. Will we be expected to know how to find the volume of a region rotated around an axis with polar graphs as well? I want to say not on the AP test. I don't think I've seen that before. But that'd be kind of cool to think about. How do we know which radius is bigger or smaller on a multiple choice question if not given the graph? So 1, you have technology since you'll be testing remote. Graph it. 2, use your number sense. Got to take some time to think about what's going to have a larger radius at certain values. Then there's a question of, well, where do the indices of the integrals when we're taking the area come from? These indices, a to b of whatever we're squaring here, it's coming from the intersection of the graphs of the equations. It's basically talking about the places that bind the region. So for example, if we wanted to find the area between 1 plus r sine theta, yellow is bad, let's use red, and outside the circle 3 sine theta, so outside blue but inside red, we need to think about, okay, there are a couple of different ways you could do this actually. But one way could be like, let's think about where are we intersecting here and in what direction are we moving? I think area problems with polar require a lot of thinking, a lot of being aware of what you're doing in the process, aware of, you can't really go on autopilot of just like, oh, they intersected and this is good because, well, how is the curve moving? We want to be going in which direction, etc. So I mentioned that there was a question of like, okay, how could we solve for other sorts of regions? So here, there are lots of ways you can do it. Like I'm looking at this and I'm like, ooh, that's kind of daunting. Oh man, like how could I solve that area with the thinking about intersections? I'm going to pause, I encourage you to pause and see, is there a way you can think of that's not finding the intersections, that's something else? Okay, so something maybe you noticed is, here's the area inside the circle. And this we can find pretty easily because this is a circle with a radius of 3. So it should be pi times 3 squared. Or sorry, not radius, a diameter of 3. Let's undo that. And then this pink curve here area of 1 plus sine, why am I writing theta? Theta, we could pretty easily find the area, just go from 0 to 2 pi and find that area. And what should we do with the pink and the blue areas? Like, where is the yellow area? Maybe you notice the yellow area is just inside pink. And so what we could do is we could take this we could do some maneuvering here. We could, instead of finding the overlap, we could find the overlap of the regions and then subtract it from the total area. And there are also other ways you could approach this. That's another beauty of math in general, and specifically finding area of polar or enclosed bipolar graphs. Alrighty, I hope you enjoyed this video. I hope it answered some questions, and if you still have more, or if more come up during the Desmos activity, please send me a message or an email. I'll see you after spring break, and I'll see some of you in person. Can't wait. Bye-bye.